Go out and see is Barry or Alison out there. Because we told them once.
Okay, good afternoon everybody. Okay, welcome to today's lecture on chemistry in everyday life. Firstly, I just want to point out the fire exits. If we do by any chance close them, I like to use the fire exits. One to your left over there, one to your right down there, two to the back down there. Just follow your teachers, maybe the people running the quickest trying to get it fast. Okay, so today we're going to have our demonstration on chemistry experiments. I'll even start fun chemistry experiments. So, we're going to have 5 different sets. We're going to start off with we're going to do chemical reactions. Okay. And this reacts with the bisulfate ion. This forms iodide, I minus. Okay? So then we just add in some sulfuric acid, and then also we're adding in some ethanol. Being added in now. Okay? So what's happening in there now? Just taking it. And we're just forming a blue band colour. Okay. So just to show you that, what happens is the iodine reacts with the starch and we get blue back colour, which is cool colour. Okay? Thank you, Joy. Okay, so we've been planning this for a long time and it's been very stressful. So now we're going to make some beer for ourselves. Okay, so we're going to need somebody from the audience to help us out. So hand up. Okay, yes, at the back.
Okay, so this is pretty much the same reaction as the last time. Except And there we have 2 pints of beer for us for later on. Thanks for your time. Okay, so does anyone know what puts the fizz in Coke or any fizzy drinks? Carbon dioxide, very good. So, carbon dioxide is pumped into the bottle and it binds to the water molecules and forms a weak form of carbonic acid. Okay, so inside a bottle of Coke we have all the molecules of carbonic acid. Okay, and we'll just show you what happens if you put Mentos into it. Okay, so what happened there was there is Arabic gum in the Mentos which makes it chewy, and when that was put into the Coke, it breaks the surface tension and the molecules break, so you're left with water in your bottle, and the carbon dioxide builds up as a gas, and therefore pressure builds up and it's released. So do you just want to see that again on a bigger scale? Yeah. Okay, we'll use the Coke we made earlier. Okay, here it is.
Okay, as Una said there, what's in the Coke that makes it fizzy is CO2. Okay, so another form of CO2 is dry ice, which is a solid form. Okay, it's just in there as little pellets. Okay, and what we're going to do is we're going to put some metal spoons into it. Hot metal spoons. Yeah, and when you put them into it, okay, and what's happening there is, because the metal spoons are hot, it's the CO2 is actually turning from a solid straight into a gas. And it's doing this, it's making the metal spoons vibrate, which is why you get the noise. That lovely screeching noise.
Want me to do it again?
Yeah, we'll do it again, just to make sure they've got the noise. You know, if you move right just to show them. Okay. You hit it up again. Okay, here we go now. Okay.
Okay, so does anyone know what's so special about dry ice? Okay, so CO2 sublimes. Okay, so that means it goes from a solid. Very good. And it doesn't go to a liquid. So we have CO2 in here, dry ice, and we're going to just add some hot water. And it goes straight to a gas. Okay, so that's pretty much the end of ours. So
Okay, next up. So that was chemical reactions, a lot of different forms of chemical reactions using gases and solids and liquids as well. Now we're going to move on to polymers. Two girls, Sinead and Sarah, are going to work you through those. Nice, guys.
Okay, well today we're going to talk to you about polymers, okay? And polymers are small molecules that form in chains. So Sinead is just going to show you what a polymer looks like. Okay? Now polymers are found everywhere around us in Coke bottles, but they're also found in your body. Your whole body is made of polymers. Did you ever hear of DNA? Yeah. DNA is actually a polymer. Okay.
Okay, so we need a little bit of help. Somebody's going to help Sarah make some custard later on. So, should I go down and have some custard? Get Hannah to mix up some custard for us for use later on in your demonstration. So while Hannah's doing that, we're going to show you some other properties of polymers.
Okay, we're going to make some slime. Okay? Because slime is actually a polymer. And to make slime, we're going to use something called PVA. And you might have heard that. That's a glue, PVA glue. So we're going to use PVA, and we're also going to use something else called borax to make our slime. Okay, so we're going to add in 5 amounts of PVA and 1 amount of our borax, and that'll make our slime. So we added in 100 ml of PVA, a little bit of green paint to make it look a bit yucky. Okay. And then we'll add in our borax. And then mix it all together. But it's also solid because you can break it apart. Okay?
Cheers.
So that's just let Sinead clean her hands there.
What actually happens in the slime is the borax solution, which are colour balls, has reacted with PVA, which is their polymer, and the chains they form a bridge between the two chains, and it means that it flows because the chains move up and down, and the polymers bridge at different places, making it become solid. Hey. Okay. How you getting on? How you getting on, custard? Get it all ready in?
Now we need 2 volunteers, okay? effect on all yours because water has no effect on it. Okay?
We're going to see how you get on with custard.
The more you talk, the longer it's going to take. Okay. Okay, next we're going to have Cole, John and Richard, and then we're going to have a bit of fun. Okay.
Oh, very fun, man. Right, okay, myself and boys, two main components in air. So I'm going to tell you what they are. Oxygen and gas. Nitrogen. Okay, well, first of all, we're going to release some oxygen. So I'll pass on to Richard.
Thank you, Cole. Hello, guys. Today we're going to release some oxygen. That sounds a little boring, doesn't it? So, what we're going to do is we're going to make some toothpaste in the process. And we're not just going to make any old toothpaste, we're going to make elephant toothpaste. Okay, so basically what we have here is hydrogen peroxide, which is what Colin is using. He's going to pour some of it in there, and John's going to pour some of it in his graduated cylinder. But I'm also going to pour it in my graduated cylinder. As you can see, it takes a while. Okay, so while the lads are adding hydrogen peroxide to the graduated cylinders, I'm also going to add something because I just feel like it. And because we're going to make some elephant toothpaste, I suppose we better make some elephant acrid, fresh toothpaste. So I'm going to add some coloured dye, and with other colleagues are going to add some dye as well. Okay guys, are we ready? Okay. John, you ready? Colin, you ready? Okay. Right, so we're going to release some oxygen here, as I said before. And to do that, we're going to add some chemical called potassium iodide, and we're going to hope for the best. So I think we need a bit of a countdown before we start. Can you guys give me a countdown? Okay, okay, guys, are you ready? Are you ready? Okay. Okay, so 5, 4, 3, 2, 1. Hold it, hold it. Okay guys, I wasn't happy with that countdown, so can we have another countdown? Okay. 5, 4, 3, 2, 1. Okay, okay, so there you have it, that's oxygen release. Okay, so basically, I'm just going to tell you, as I said before, we had hydrogen peroxide, and we added that to each graduated cylinder, and then we added some washing up liquid. And the purpose of the washing up liquid was to capture the oxygen as it was released during the reaction. But we just had our washing up liquid in the graduated cylinder with hydrogen peroxide, and nothing happened. But when I added some of this stuff along with Colin and John, the reaction shot up. So what we added was potassium iodide, and that was the catalyst, and it sped up the reaction. Okay, so I'm now going to hand you over to Colin.
We've got a problem now. Piece of oil on 2 days. And I don't actually know what hammer the nails in. Just, I don't know what to do. Just, does anyone have any suggestions, though?
I know, what do you think?
Hammer. What do you mean?
Try use banana.
Banana. Banana do it. I won't do it, John. Won't. I won't do it.
Right.
Won't.
Banana will go.
Alright, we get 2 people up and see what the plan is. Right, Stephen's here, right? Now, Steve, put them on. I can get messy, right? Put them on. Right then? Sorry, I want you to put that head hammer on nail on your hand, okay? Yeah, hammer. Just keep tapping. John, help me now.
You've been here as well, right? So what we're going to do, give the fella a banana and give the girl another banana. And see who's going to hammer the most, right? So we give both of them close, so it doesn't make a mess. Trying to bite close. Right, come on. Right. Right, so I want Kate to win. Right, 1, 2, 3, go. Come on. Wait, quick look. 1 nail still left in it. Whose nail was it? Kate's nail. Right, that's the nail, lovely. Thank you.
Sound. Don't talk about what happened there.
Okay, guys. Basically, what happened there was our volunteer was using a banana that was, I'm sure you all guessed, frozen. And the reason it was frozen is because it was dipped in liquid nitrogen. Now, liquid nitrogen is a very, very cold gas, minus 200 degrees Celsius. Okay, so once the banana was dropped in the liquid nitrogen, it took all the heat from the banana and more or less froze it solid. And as you all observed, it more or less could hammer the nail into the wood. It acted like a hammer because it was more or less rock solid. So that's what happened, and I think I almost say a few words. He's very hungry.
Stop. Only that's a
Oh,
you know.
man. Shut up. No one made the instead, and all goddamn morning. See it this way, right? So all he has to do is, right, we'll try to put the water balloon into the liquid nitrogen, right? See what happens there.
That's not.
If it will, we're going to give him an egg, right? See if it works.
Get rid of them balloons, isn't it?
Get rid of the balloons, so you're giving that egg, right? Right, so we have 3 balloons in here. 1, 2, 3, 4, 6, 7, 8 balloons. And Carl here wants to put them in that canister. You think it'll work? No? Yeah? Yeah, no? Right, and down here. Right. 1 balloon. 2 Right, so if we got the 8 balloons in, there's a whole balloons, a whole table. You'll see what happened now. His name is Colin, is it? Colin's going to... we left the string hanging out there, so he's going to pull the string. Go for it. Come on, baby, come on. 1, 2, 3, 4, 5, 6, 7, 8. All the balloons came out. Look what's happening.
Making a mess.
It's making a mess, yeah. What's happening?
Gonna fly again.
What? So what happened? Can anyone tell me what happened? Someone stand up there and tell me.
Baker.
Guys, I don't know, but I thought it disappeared. He obviously didn't. So basically, what happened was, once we added the liquid nitrogen, as we said before, was so cold that it literally took all the heat from each balloon, the gas molecules in the balloon, and that was why they decreased, and that was why we could more or less put more of them into the liquid nitrogen. So once our volunteer took them out of the liquid nitrogen, there was more heat in the surroundings, and consequently there was more heat in the balloons, and that's why they expanded.
John was right, made an egg. So basically, the water balloon went into the liquid nitrogen. Liquid nitrogen is at about minus 200 degrees.
Throw it out.
And, no, I'm not going to smash it. There we go. Why? Degrees. Okay. Right, we're going to move on now to the final finale. We have we want to show you 3 states of matter. Okay. So okay. So can anyone name the 3 states of water? Yeah. So liquid, water, and what's solid? Ice, yeah, and steam, water, vapor is condensation, yeah, very good. So, here we go.
Let it go. He's very...
Okay, you can see we still have we have the water vapor here, the gas, okay, and ice. John, you know and we still have the liquid. Yeah, so John's going to show it in more information. We should get some ice. That's very good. If you can hear it, it's crackling, you can see it's freezing. It's going to go on forever. Anyway, you can get the idea. There's ice there now. It's filled up with ice. There we go. There's ice. Okay, we're back over the end. Thank you.
Thanks guys, John, Paul and Richard. Okay, next, so we saw some gas work there. Now, John and Fiona behind me have a delegate set up, so while they're setting up, I'm just going to introduce what they're going to do to you. Basically, they're going to work with you the properties of gases. How they react, how they work, if they float, if they fall. So that's what they're going to do. John, ready?
Right, well, hello everyone. As Daniel said, we're going to be dealing with the properties of gases. And myself, John, and Fiona here, we're going to first show you a setup. Right, in these 3 beakers. come across before, the dry ice. Come across it several times today. Now, what we're going to do is show you sublimation, which you've seen before, but show you how it affects different frozen quantities. Like, we have normal ice here and hot water. So what happens when we add normal water, hot water into ice? If I get it right, it melts and it's boring. And we don't like that at all. So if we have dry ice here and we add some cold water into it, what will happen? See, all seen it 2 or 3 times before? It'll melt. CO2 now. It'll sublime. But again, that's another very boring reaction. We don't like that at all. We want good, fast reactions. So we'll try some hot water because the boiling point of CO2 is so low that the boiling water should make it go very quickly. Yeah, we like that sort of reaction. A good, fast reaction that spreads a lot of the chemicals everywhere. Right, I'm just going to put this out to the side now. And let that build up. We'll come back to that later on. Now, you're all probably wondering what this contraption here is. What does it look like, first of all? It's taken DCU years to come up with this contraption. Research and development spent millions of euro on it. It's basically a tap. That's all it is a tap. But a fun kind of tap. Because we're dealing with the properties of gases, and we thought, how can we capture gases? What's the best way to capture a gas? A bubble, exactly. Because bubbles are clear, you can see into them. You can have fun with them, play around with them. So, what we're going to do is we're going to put some dry ice into that, the empty Coke bottle, which we spent all last night drinking, worrying about this, and some bubble solution. Now, as you can see, we have a bit of tissue around the end of this pipe. That's just to help the bubble solution stay attached to the pipe and not drop off before anything. You can see the CO2 already melting. That's because it's at room temperature. But if we add in some hot water, if we add in some hot water, it will sublime, and hopefully the gas will shoot out and close this hole.
Come on, you can do it.
So we get a bubble. Nearly. There's too much CO2 going into it now, the pressure's too big, so just now. Now, as you can see that CO2 is coming up through the pipes. We were hoping that would actually do that, we didn't know if it actually made it. Right, the CO2 is going up into the bubbles, and I'll hand you over to Fiona to describe it.
Okay, as you can see here, what's happening is the CO2 evolves faster than your normal bubbles because CO2 is denser than air. So for some reason they also bounce because they're stronger. We put some glycerine in our bubbles. And that will go on for a few minutes. Now, we're going to move on and show that bubbles will also float on the CO2 and go back to saying that air bubbles are less dense than carbon
Now I told you that the CO2 was more dense in air, so as you can see here, we put plenty of CO2 in here. It's staying in the bucket. It's not going up, shooting up. So exactly, we have incredibles to play along with today.
extra strong.
Oh yeah. So we're going to show you that the bubbles should float. You can see that they're floating on the CO2 because they're made of air, which is less dense than the CO2. And you can see there that the air in the bubbles is floating on the CO2 on top of the bucket. Right, we're going to...
What will eventually happen is you see the bubbles, they will slowly sink to the bottom when the carbon dioxide will fuse into the bubbles and they'll sink down, and eventually they will freeze from the CO2 before they become ice. Okay? Now we're going to move on to another gas. John's going to show us a bit about helium balloons. Now we all know what helium balloons do.
Now we chose this experiment because of the complete and utter mess that we would make all over the floors. You can see bubble solution dripping all over.
And the fun.
And the fun of it, exactly. So we're going to touch this balloon, and hopefully, now this wasn't very successful earlier on, so you're going to have to, hopefully, see if you're acting up over there. You're going to have to cross your fingers for us here and hope that this blows a bubble. We'll add some helium into it. Just bear with us for a moment. Right. Now, hopefully, we can get some of the helium into the balloon. There we go. It shows. We're lucky. We'll rise up to the ceiling. There we go. That shows that helium is less dense than air. As you can see, our little stick man is very happy there with himself because he's gotten a helium balloon and it's floating back up to the sky. Now, move on to a third gas here. You bear with us. Now this group alone were allowed to use a lighter, which mightn't have been the best idea. So we're going to see the effects that different gases have on a flame. See how much fun we can have with this. So we had some bubble solution into the graduated cylinders there. Now, first of all, we're going to use our good old friend, carbon dioxide. So we're going to get some of the dry ice and throw it in, see what effect it has on the bubble solution there. Now we're after adding hot water in, so you can see it's just like the snake, and we've got a flame. So, what do you think will happen if I put this flame near the carbon dioxide? It'll blow up? Who says it'll blow up? Put up your hands if you think it'll blow up. We have one very brave girl down the back there who thinks it'll blow up. Oh God, sorry. Right, well, we'll put the flame here down there to see. Right. Right, settle down, right. We have our flames here, and the bubbles full of CO2, so you think it'll blow up when you bring the CO2 near it. So, oh no, nothing happened. The flame went out by the CO2. Carbon dioxide does not conduct the flame, as you can see there. The flame goes out. To prove that, it doesn't do it, it blows out the flame. We have some butane here. Right, so to prove that it was actually the bubbles, it was actually the CO2 and not the bubbles. Right, just get yourself to set up. Give me a tell everybody what happens. You're just have to happening to the candles? They're gone out. That's the CO2 coming out of the flames. Now, we're going to put some butane in and see what effect this has on it. Properties of gas.
Okay, thank you. Okay, thank you, gentlemen, the owner. Okay, now the next group. Acids and bases are not that boring. So, I'll do a quick demonstration for you now on a few acids and bases, how they react with each other, and what the results are. So, what have you got first, Mandy?
As you know, mostly acids and bases are clear liquids. You can't really tell them apart by just looking at them. So we're going to show you how an indicator can work to help you see the difference. Okay, this is just a bottle of tap water. Put a small amount of indicator into it, and you get this nice green colour. That's because at a nominal pH of 7, which is what you get with Dublin Corporation tap water, that's the pH. That's the colour that this particular indicator shows. Now, just transfer some of it into each of these beakers. Okay? Daniel, just line them up here so that folks can see our colours. Okay,
You went in there.
I'm going to add a small drop of sodium hydroxide. It's a base. Just going to pour a small drop in here, see what happens to the colour. There you go. Wow! Okay, see what you can do in there. To let you know which is which. The acid is giving us a nice yellow colour and it stays and it behaves itself and no changes. And the base has given us a nice blue. Now, this lecture is supposed to be about science in everyday life. So I want to investigate what this product, can you see it? Isodol. It's an antacid. And we want to see what way that will behave if I put it into an acid solution. And Daniel is working away on getting an acid solution ready for us. So while he's working, I'm just going to get something organised.
Okay, so basically what I have here is a magnesium solution. Now it's magnesium hydroxide, so that's the base. So our base colour over there was blue, so we kind of a greeny blue here, with the universal indicator in here. So the indicator shows the colour range of which is an acid or a base. So we see here, our base here is blue, our neutral pH is 7, that's green, and then our golden yellow colour, that's our acid. So now, I might put my acid in here. So I'm swirling this nicely.
Getting that nice acid colour.
Yeah, so now just put in a little drop and it turns red.
Chuck it in there. Okay, it's red.
Yeah, it's red.
Yeah,
Oh.
I need
Put more in.
put more in.
Yeah, Daniel. Well, Daniel.
Red.
There.
Right. Okay, now we need to get a sample of that. What's going on here? All right. Okay. Daniel, what did you put in there? Yeah, what was in it already?
Magnesium hydroxide.
Okay, magnesium hydroxide and you put it into acid.
So yeah, so it's base and an acid.
Where are we getting the colour from?
Well, the red colour, the yellowy colour is the base. Yellowy green. That's the basic colour, and then when it turns bright red, the pink.
But how
That's
are we
the
getting
acid.
the colour? Did you put an indicator in there?
Yeah, the universal indicator.
You put some indicator? Okay. Right, we've got red again.
Right.
And now it's gone.
Oh, you want?
Okay, I reckon there's something astray here. This is very good. How much magnesium hydroxide did you put in?
Plenty. Probably copies of this.
Did it all dissolve?
And it's swirling.
Okay.
Well, I had it swirling in
Okay, now I have that. The magnesium hydroxide is acting as a base. And when Daniel made it, he was, being eager, and he put in lots. And this is all cloudy here, all dissolved. And as it's dissolving, it's using up our acid. So I tell you what we do, get some out of there quickly while it's still red, and get it in here. We'll see if we can do that with the ice drop.
Okay.
That's what I said.
Go on, Daniel.
Quick. Okay, at least it's staying red this time. Now let's see if our rice roll will do anything for us, because it sure as hell will do something for us. Here, hold on.
So what is it on doing now?
Huh. It's not doing a lot.
It's fizzing.
It's fizzing.
It's buzz.
Oh, that was a bit of a disappointment.
Yeah. Things wrong from here. That's not what I heard.
But this one's dead red.
Yeah, that's big.
That's a bit disappointing. I think we just have to forget about that. I'm upset at. No, I'm too upset.
Cheryl. Sorry.
What do you want?
I don't know. Surprise me. Something nice.
All right.
Something nice.
Okay. I'm gonna make 4 drinks, but there's only 2 of us. So, anybody want a glass of water? Okay. 2 girls in front here can have a glass of water. So what do you want?
I don't know. Something nice.
Right.
I know.
I'll give you a cranberry juice.
Okay.
Where's your red beans? Okay. Glass of water? Glass of water, alright. I'll do the same to you, Granny.
Okay.
And glass of water?
Yeah.
Yeah. Right. Okay. Well, we'll try first just to make sure it's alright. Have it.
Here, I'll bring it. Okay.
This was cranberry juice.
Yeah, give it the whole
Imagine cranberry juice.
No. I'm afraid not. No, I can't drink that.
What?
I can't drink that. It's horrible.
Cranberry juice?
I'm changing my mind.
Hey, what do you want?
I think we're going to give you water.
Water, alright.
Yeah.
Nancy, what you doing, bro? You did something while I was over there.
No, you said it was cranberry juice. That was it,
It
mate.
was. She put it in while I was over there.
I know he's trying to poison it.
I just have a glass of water myself. Yeah. So that's it.
What happened to the cranberry juice?
We're not having any cranberry juice.
What are we having?
We're all having water.
We're all having water, all in one bottle.
And that's it.
And that's magic.
Yeah.
Daddy, thanks. I was out last night.
You won.
I was out last night.
We're supposed to be getting ready for this.
Yeah, we're going to do
What are
it.
we doing here?
Hey, you put Naki seltzer in the water.
This is a science demo. Science, so
All
we're
right.
doing here.
You're breaking up the Alka-Seltzer into its components.
Which are?
An acid and a base. That's what we're doing, acid and base.
Oh,
It
okay.
would be a bit stupid if it wasn't an acid and a base.
Okay, so we've got a solid acid and a solid base
Yeah.
in the tablet, and,
Yeah.
and they go into the water and they start doing what?
And they become soluble, they become an acid and base solution in the water, and then
What's this one?
carbon dioxide makes it lovely.
Makes it easy to drink?
Yeah.
Right, grand.
Things like fizzy water. Otherwise it shouldn't be.
What's that going to do for you after you drink it?
Make you throw up, so you get all the stuff out of it.
Go on.
No?
No, that wasn't the answer.
Okay.
Okay, what we have here is a mixture of acids and bases, and when they mix together in the glass, they behave like buffer. So that when you take it and you drink it, the buffer acts to absorb some of the excess stomach acid, which is making you feel unwell. So what we're going to do next is give you an idea of how the buffer works in the lab.
Right, what are you doing now?
Okay, will you put about 50 mils of sodium hydroxide into each of these?
How is it? One more sodium hydroxide.
Okay, how much is going back? About 50 mils in each?
Yeah, 50 mils for me, 50 mils for you.
Your promise?
It's good.
Okay, well the next thing we're going to need is an indicator so that we can see what's going on.
Right. Put this in here. Purple.
Is it purple? This sounds like a song. Have we got a song called Purple Rain anywhere?
Right.
Are we able to see the colours here? Okay. What we
Everybody
want-
see the purple colour?
What we want to do here is demonstrate the action of a small quantity of buffer in here. We've got the same amount of base in each, same amount of indicator. I'm going to put a tiny amount of buffer into this one. Hang on a minute.
Buffer was what was in the Bicerol and the Alka-Seltzer. There's constant pH, so it increases the pH of your stomach. Your stomach is acid. Acid fluid. My Lisa.
Okay, so now, where's the acid gone? Daniel, I want you to add stuff in here until you get that to change colour. And just make it change. Don't go too far. Okay, we're getting it going. It's looking good. Yeah.
I mean,
See what will happen again a little bit more. Okay, nice and green. Oh, wow. For a tiny additional drop of buffer, just
always do.
less than than 2 pipettefuls, that's how much extra acid it took to make the base change from a base solution to an acid solution. And that's how the bottle will work. Thank you guys, I hope we had some fun here today.
Okay, so that was all a single demonstration. Now, you don't know this, but we're all a class. We're all the same class. So what we're going to do for you now is we'll join the demonstration. We're going to finish off with a huge demonstration. Okay. Give us a shoe. Okay, does anybody have a piece of paper? Can I just get a piece of paper off of me, please? Okay. Thank you very much. Thank you. Okay, what I'm going to do now, I'm going to burn paper. Okay. So what I have here is ethanol. Now, ethanol is basically the alcohol in every alcoholic drink. Okay, so just ethanol in here with a piece of paper. Get this going. He's not getting this. Yeah, I know. Okay, so here. Alright. I'm gonna burn 10 euro. So in here. Who's ethanol? Okay. So ethanol. Take it out there. And we're burning money. There, see the slide flying there? Let's do it again, let's do it again. See a slide flying? Not that much. You broke me, Lord. No, oh, you're breaking. Oh. What the hell? I want to say thanks to the audience for coming. No problem. And thanks to everybody here for the demonstration. We hope you enjoyed yourself. Now go and do leading to chemistry.